So next, it is my pleasure to introduce Greta Panova, who will be telling us about structure constants.
Thank you very much. Thank you very much for organizing this event, even after happy that we are here 2 years later. Okay, so do you actually hear me? Microphone. Do you hear me now? Okay. All right. All right. So that's also the first time I'm talking in public without a mask for the last 2 years. Okay. So what is this talk about? Actually, this microphone seems to be going on and off. Or is it because it's moving? How about now? Okay, I don't know. No.
Okay. Yeah, I don't know. Sorry.
So is it okay now? Okay. Okay, so what are these structure constants? So these are very classical quantities that date from like 100 years ago. It has to do with, again, very classical topic that actually nobody really mentioned it so far. My surprise, but we're gonna be talking about irreducible representations of the symmetric group and the general linear group. And as you probably know from undergraduate algebra, the irreducible representations of the symmetric group, these are the Specht modules. They are indexed by partitions lambda of n. Their dimension is the same as the number of standard Young tableau. So I hope everybody here knows what a standard Young tableau is. And sure functions in a moment. And the general linear group, the irreducible representations, are also indexed by partitions. This time, these partitions are limited in their row lengths by n, the size of the matrices in the general linear group. Okay, so what can we do once we understood these representations? There is a typo. This should be V lambda. So we can take tensor products of these representations. They are also representations of the same group. We can decompose them into irreducible. So for the GLN, if we decompose the tensor product of two irreducibles into another irreducible, we get the Littlewood-Richardson coefficients, and which are also written over on the board in case you forget what it is. And the same thing we can do about with the symmetry group. So if we take two irreducible SN representations, we can take tensor product. The symmetry group is acting diagonally on this tensor product, decomposes into irreducibles, and the multiplicity of each irreducible is this Kronecker coefficient. So should not be confused with Kronecker delta, which so sometimes we get these interesting citations from chemistry papers about the Kronecker delta somehow showed up in their paper, and so these are the Kronecker coefficients, G lambda mu nu. So by definition, these are going to be non-negative integers. So that's already a combinatorial problem. And the last thing I will mention, but Anschilling is going to talk about this in later, so I'm only going to define it for the purposes of this talk. The composition of general linear group representations, and in this case, I will only do symmetric powers, so it's nothing too fancy. So we can decompose general linear group representations. We can factor this also into irreducibles, and these are going to be the plethysm coefficients, A lambda dn. So these are special, the more general plethysm coefficient is defined over there, but this is all we're going to need here. So this is what what we call structure constants. So of course there are many more depending on what kind of objects you want to study, but these are already a handful. So how else can we define them? If we forget about representation theory, we can define them with symmetric functions. So I was hoping somebody would have mentioned sure functions so far. This is algebraic combinatorics, right? But no, so I guess I'll have to be the first one. Does anyone not know what a sure function is? It's the character of the general linear group representation. Okay, so sure functions, of course, have a combinatorial formulas in terms of semi-standard young tableau and all this. We are not going to get into any of the details here, so we use it as a black box. But in principle, you can do elementary calculations using this type of formulas. You can extract these coefficients because the sure functions form a basis and all these things. But there is one thing that these symmetric functions lose when you look at it like this. We don't know anymore that these coefficients are non-negative. So if we just use these formulas to extract these coefficients, we cannot really get this. And this is the heart of the problem. And also, so these are these formulas. There is also a way to, of course, by definition, to compute the Kronecker coefficients with the irreducible characters of the symmetric group. For the irreducible characters of the symmetric group, there is some sort of a combinatorial formula, but it's an alternating formula. So we are summing over some structures called Murnaghan-Nakayama tableau. So we and for each of them, we have -1 to the height of the tableau. So, and these numbers can be arbitrarily large, positive, negative, and so on. So this formula is also not really combinatorial. So yeah, you can plug it into a computer if you have the time to wait until the computer computes the characters, which already takes some time. But you combinatorially, it's very difficult to extract any information out of it. So the best thing we know, so still with like almost 100 years later, is the Littlewood-Richardson rule, which actually took a while to be proven rigorously, but that this Littlewood-Richardson coefficient is equal to the number of, again, some type of tableau, shape lambda over mu. And I guess in this case, type lambda. Here is an example of how this tableau look like. So there is a combinatorial rule. We are doing these fillings. Okay, so we count all possible such fillings. In this case, there are 2, and then we get the Littlewood-Richardson coefficient. So that's all good. That's a beautiful rule. So what do we get for the Kronecker coefficients? And when Murnaghan introduced them in 1938, he asked for the same thing. So is there a combinatorial rule to compute this Kronecker coefficients? And then Stanley listed this as number 9 or 10 open problem in his big list. And the other one is the plethysm coefficients. So that I just mentioned. And the problem is phrased very, very vaguely. Find the combinatorial interpretation. So is there a family of discrete nice objects indexed by these triples of partition such that G lambda mu nu is equal to the number of these objects? Okay, so here is an open problem, right? Okay, so where does the motivation come from? Well, actually, the Littlewood-Richardson coefficients are a special case of these Kronecker coefficients, as this theorem of Murnaghan shows. So there may be some hope. So since then, for the past, okay, let's say 84 years, this is really the progress in the direction of combinatorial interpretation. So first, when both mu and nu are hooks, then if one partition is a 2-row, but then the other one, another one has some other restrictions and so on. So maybe the most general case is due to John Blazek. When one of the partitions is a hook and the other two are arbitrary, there is actually a combinatorial interpretation in terms of certain types of tableau and with so and such restriction. And there are some other special cases that some of them I will mention in a moment. But basically, that's it. So the Kronecker coefficient is just a black box. So from then on, what do we do with this? So the first thing is we need to actually be able to formulate the question about the combinatorial interpretation in a more precise way. So Igor will talk about this tomorrow in more details, but I will, in order just to explain what's going on here, I have to talk about complexity. So computational complexity, let's see if I can explain this in 1 minute. So imagine your favorite computer or Turing machine in general, or whatever computational device we're trying to solve a problem. The input has n bits, and then we have some problem to solve. So that can be anything. So compute some numbers, find out whether a graph has a Hamiltonian cycle, all sorts of things. And there are basically two classes of problems. There is the decision problems, where we are asking whether something exists. So if the input is a graph, does there exist a Hamiltonian cycle for that particular graph? And then there are the two main classes that you probably have heard about, the P and NP. The classes P, these are the classes of problems where you can find the answer in polynomial in n times. So there is this parameter here, the size of the input, and everything is defined in terms of the size of the input. And this can make a big difference actually for what the answer is going to be in the end. And the other class NP is the class of decision problems, where if the answer is yes, then we can check it in polynomial time if this is true. So if I give you a graph and I say yes, it has a Hamiltonian cycle, we can verify it by just me giving you the Hamiltonian cycle, and you can actually check in linear time or in the size of the graph, you can check whether this is really a Hamiltonian cycle. So you can actually do this. And naturally, P is contained in NP. So the other counterpart are the counting problems. So when, again, this example with the Hamiltonian cycle, we're basically going to ask how many are there. So if you're given a graph, how many Hamiltonian cycles do we have? And again, so we have the two complexity classes, FP, where we can just find the answer in polynomial time, in polynomial in the input size, and sharp P. And sharp P is the important thing here, is basically the counting analog for this NP problems. And the example with Hamiltonian cycle, it's actually one of the NP complete problems. So it's the universal representative of this class NP. So that, and this is how we compare complexities, by reducing to some complete problem. Yeah. This is the class co-NP. So there's a different class, and we don't know whether these two classes are the same, and they're probably not. So that's a certificate for the negative case that you're asking, and that's another class. Both P's contained in NP and co-NP, but if P and co-NP are probably not the same. So it's, of course, everything is conjecture here. So with P equal to NP, this is our big hypothesis and the big problem. And so yeah, we're not going to answer this today. So, but another open problem. Okay, so why are we talking about this now? So there are basically two motivations. One is we're going to use sharp P to actually P, NP, sharp P, and all this to actually explain how hard these structure constants are. So this is a way for you to figure out how difficult a problem is. It's a formal, this is for theoretical computer science, it's actually a formal way to describe this. So let's see what we know. For the Littlewood-Richardson, they are computing them is in sharp P. So here, what is the input matters? How do we encode these partitions lambda, mu, and nu? If we encode them as binary, in binary, so basically the size of the input is log of the size of the partition. Then the Littlewood-Richardson coefficients are what's called sharp P complete. So they're as hard as any sharp P problem. And what is the certificate? Well, the Littlewood-Richardson tableau. So so we are counting this Littlewood-Richardson tableau, and if the Littlewood-Richardson coefficient is going to be non-zero, I can just prove it to you immediately by showing you one tableau. So what about actually positivity? And this is a very, very special situation that deciding positivity for Littlewood-Richardson is actually polynomial, and this is due to the saturation conjecture proof of Knudsen and Tao from 20 years ago. That basically the problem boils down to finding whether a polytope is non-empty. Originally it's about finding an integer point in the polytope, but in this case it happens that if the polytope is non-empty, it always has an integer point. So, and finding if a polytope is non-empty, this is a linear programming problem, and it's easy. So what about the characters of the symmetric group? So first of all, a priori, they are not even positive integers, so they don't actually fit the paradigm. But we can still ask the question of is this zero or not, and deciding whether a character is zero or not, even in unary, is already NP. So it looks very simple. There is a problem that it already contains all the complexity you want. And what about the Kronecker coefficient? So the one is computing them. The other problem is their positivity. And so first of all, deciding whether they're positive is NP hard. It's not NP complete because we cannot show that if the Kronecker coefficient is bigger than 0, there is no polynomial certificate, at least not that we know of, that we can actually verify that this is true. Yeah, P is the class of the difference of two sharp P functions. But we actually do not know whether the Kronecker is in sharp P, which is more or less the formal definition of combinatorial interpretation that I mentioned. So here is an open problem. Are the Kronecker coefficients in sharp P? And I think at this point there is actually some evidence they are not. And there are of course some hypotheses. So it's okay. So now if this whole situation is so hopeless with the Kronecker coefficients, what are we doing then? So So there are still questions that can be answered. So the fact that they are difficult, they are hard, doesn't mean that we cannot do anything about this. So here is one conjecture, so another open problem, the tensor square conjecture, which was formulated by Jan Saxel in 2012. Yeah. I like the runtime. So the question was, what's the best runtime algorithm for computing the Kronecker coefficients? And it's, I mean, it's more than exponential, I would say. And so I guess depends on how you encode the input. So if you have just fixed number of rows, then it's actually polynomial. But for fixed number of rows, but if the partitions are growing, then it's super exponential, like from what we know. Okay, so here is this Saxel conjecture. There is a very concrete open problem still. So this followed after Saxel and his collaborators. They discovered that for simple groups of Lie type, finite simple groups of Lie type, there is always an irreducible representation where if you take the tensor square, it will contain every other irreducible representation. And the question is, does this hold for the symmetry group? So Jan Saxel conjectured that if we just take the staircase partition and we take it, then the tensor staircase, then it's going to contain every irreducible representation. Note here that we need to have symmetric partitions because otherwise they would not contain the sign representation. So there are some details and properties of Kronecker coefficients. So what we figured out, what has been figured out about this? Well, some very special cases as usual. So that I guess the most general lower bound comes from this character evaluation, but this is not super useful. So this absolute value of the character evaluated at the hook length of the partition lambda. But the problem with this approach is that the characters are very often zero. So this is not, especially for large lambda, it's going to be almost immediately zero. So this is not a very useful lower bound. Then Christian Ickenmeyer showed with other methods that is particularly for the staircase partition that the tensor product will contain all partitions, irreducible representations whose partitions are comparable in the dominance order to the staircase partitions, but this is still not many actually of them. And then there was a probabilistic argument that this Kronecker coefficient is positive for almost all in some sense partitions, but still, I mean, there are a lot of ones that are being omitted here, and we don't really know how to approach this. And so this is one positivity problem, and in this result. So other positivity problems, they were and other results, they were related to the application of Kronecker coefficients to what's called geometric complexity theory. So here is a positivity result for almost rectangular partitions. So two rectangular partitions with longer first row and whatever else. Then so this turns out to be almost always positive. And the reason this particular Kronecker coefficients were of interest is because of what's called geometric complexity theory. And okay, so now, yeah. 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 So staircase for this particular, if n is a triangular number, but otherwise there are still actually. So for if you cannot describe it in this way, we have actually. I'm not mentioning them here, but we do have conjectures of the other cases, and actually it's a lot more general than this. So it's not, the staircase is just a nice partition which has a large dimension, which is actually needed for this to work. But yeah. So yeah, otherwise it's not going to contain the sign representation. Yeah, so the sign representation, when you tensor a irreducible representation with the sign, you just flip the diagram. So that's we do need the symmetry here. I think so. Yeah. Does the conjecture fail when n equals 8? Yeah. I think from the calculations, but I should say that for small, the problem with Kronecker coefficients is that people were computing them for small values, getting a lot of zeros and making conjectures which completely fail later on. So do not be misled with small values. Yeah. Yeah, so we did actually, there was a student, the figure checked it for up to 20 maybe, so yeah. Okay, so now I'm going to change a little bit the direction here, and I'm going to talk about geometric complexity theory, which a priori has nothing to do with Kronecker coefficients, but we will see what happens later. And the reason I will mention it is because it is another direction which uses this type of structure constants and this type of combinatorics, and also is another source of open problems. Although I will not be able to phrase them in an elementary way. So today, okay, so let me tell you a little bit about this geometric complexity theory. So this has to do with the algebraic version of P versus NP. These are called valiant, Leslie valiants, P and VNP. And instead of doing Boolean operations with 0s, 1 on a computer, we are going to compute polynomials. So the inputs are going to be constants, arbitrarily large constants from our field. From what I'll be talking about, the field of constants gonna be the complex numbers. And then and we are inputting variables, x1, x2, and so on. And we have elementary operations. So the gates, the operations are plus, minus, products, division, and so on. So we are going to look for the smallest possible circuit. So basically a circuit is something like this. So sequence of operations in this basically graph, which will output at the end when you pass everything through the nodes, we will get our polynomial. So instead of solving a problem like compute Littlewood-Richardson, we're going to actually compute polynomials formally with this algebraic circuits. And again, so there is a measure of complexity, the smallest possible number of gates that we need to compute a given polynomial. So now the complexity is associated to a polynomial. And there are two classes which correspond to P and NP, VP and VNP. So polynomials that can be computed with circuits with polynomially many in N is the number of variables, and also the degree of the polynomial will also need to be bounded here. And then there is the class VNP, which also looks like NP, where the polynomial is a sum, exponentially large sum, over polynomials, which are actually polynomially fast to compute. So this is more or less the formal definition. And of course, what is the big, so the big problem is VP equal to VNP, but if you want to have some connection to the P versus NP, so here it is. So if it happens that you prove VP equals VNP over a finite field, so the constants involved are from a finite field, then P is actually going to be equal to NP. And or if we work over the complex numbers as we do, then we also need the generalized Riemann hypothesis to hold, and then we can say that P is equal to NP. So there is some connection, but it's not immediate. And as usually, dealing with polynomials is actually simpler than just arbitrary circuit. So this is what people try to actually prove. So how does this geometric complexity theory work? So since we are in the world of polynomials, we can apply a lot of algebraic tools. So the first thing we need complete universal polynomials for the two classes. So for the class VP, we will use the determinant of an n by n variable matrix. This is a universal polynomial, meaning that means two things. Every polynomial which is in VP, we can compute as a determinant of a matrix with affine linear entries of polynomial sizes. So maybe I should write this down, but Alex had a question. No, it doesn't work that way. Okay. So okay, so I'll explain this in a moment. So we have the determinant and the permanent of an, again, in this case, m by m matrix. The permanent is like the determinant except the sign. So and somehow these two polynomials very similar but completely different in their behavior. Why? Because determinant is easy to compute because of row reduction in linear algebra will take you n cubed at most time to compute the determinant, and the permanent is what we know is at least exponential. So I'm going to skip a few things, but basically, so the permanent is a universal polynomial for this class VNP, and the conjecture that VP is not equal to VNP would follow if we show that the permanent is not equal to a determinant of a matrix with affine linear entries in these variables x11, x2, x12, and so on. For n, so this n, the size of the matrix, it should not be. So this does not hold for any n of polynomial size of m. So n should be super polynomial in m, and the size of the determinant that you need in order to compute your polynomial is called determinantal complexity, and is also and it's polynomially equivalent to the polynomial being in VP. So this is a measure, this size, the minimal size n that we need here in order to compute a polynomial is actually a measure of complexity. And we want it to be super polynomial so that we actually distinguish these two classes. So now what one can do is apply all the symmetries that we have. So the determinant is of course the same if we plus with a sign and so on. So so one can, instead of just looking at these two polynomials, we can act with the general linear group over the entries in these matrices, and then consider these two. So these are called orbit closures of the set of points that we get under this action, and then instead of distinguishing the polynomials, we can distinguish this orbit closures looking at the ring of rational functions on them, and we need to show that basically the permanent is not contained, the orbit closure of the coordinate ring orbit closure of the permanent is not contained in the coordinate ring orbit closure of the determinant for n polynomial of polynomial size. Or in the other formulation is that if the permanent is contained in the determinant, then n has to be bigger than polynomially sized m. And now we can apply algebraic geometry and representation theory to this orbit closures. So we have the action of the general linear group on these are modules, GLN squared modules. So we can factor them into reducible representations. And if we want to compare two modules, if one is contained in the other or not, we can actually just pick the multiplicity of one particular irreducible component and compare just the two numbers. And if we do that and we get an inequality in the right direction, then we are all good. So this is what's called obstructions, are these representations for which the one multiplicity is smaller than the other. And if such thing exists, then basically for n bigger than polynomially sized m, then we can actually say that VP is not equal to VMP. So here is actually an open problem. So find the lambda for which, for lambda dnm and so on. So for which we have such an inequality. And because these multiplicities are complicated, and I'm not going to write them down, but in principle, they are related to all these Kronecker and plethysm coefficients. It's just a more complicated sum. So then if delta is actually 0 and the other one is non-zero, we call that lambda is an occurrence obstruction. So there is a reducible representation which doesn't show up in the determinant, shows up in the permanent, and then we can distinguish even better. So the conjecture of GCT, the wishful thinking conjecture of GCT was that one can actually find occurrence obstructions for n bigger than polynomially sized m and solve the problem. But unfortunately, that turned out to be false. So there are no occurrence obstructions for n bigger than m to the 25th. But then the question still remains, are there actual multiplicity obstructions? So let me just briefly mention how this is related to Kronecker coefficients. So the way it's related is that the Kronecker coefficient is an upper bound for this delta. Kronecker coefficient lambda n to the d, so this is the partition n d times. And another n to the d, and the coefficient for the permanent is bounded by this plethysm. So of course, these are only upper bounds, so we don't really have a nice explicit lower bounds for this coefficient. But this is so that there was a source for this. So another conjecture that instead of looking at the delta, we can look at the Kronecker, and if the Kronecker coefficient is 0, and this gamma is actually non-zero, then we're all good. But unfortunately, what turns out is that all these Kronecker coefficients are actually positive for all partitions and values of n and m of interest. And in fact, what came out of using the complexity, the geometric complexity theory, we actually got a corollary that the Kronecker coefficient is greater than or equal to the plethysm, and I have no idea how to prove this just from the representation theory point of view, or even or any other definition. So that was an interesting corollary. So if you want to prove this in some more combinatorial way, this inequality, that's another problem. So how this proof work? So at least for in this case, if we don't know anything about the Kronecker coefficients, what can we actually do? So there are several steps. So first of all, we need to characterize which representations show up in the coordinate ring orbit closure of the permanent, and this happen to be partitions with length at most m squared, because we have m squared variables in these polynomials, because of the degree of the polynomial and that we are homogenizing it in a certain way, we need also to have lambda 1 large. The first part of the partition should be large, and then basically for all such partitions with a sufficiently long first row, we can actually show that the Kronecker is bigger, and the way bigger than 0. So the black box way of working with Kronecker coefficients, it uses a lot of this semi-group property. So if we have two partitions, two triples of partitions for which the Kronecker is positive, then if we sum these partitions pairwise, sum them partwise, then we also get a positive Kronecker coefficient. So this is called the semi-group property, and the only proof that we know is through representation theory, and it's not representation theory of the symmetric group, but using Schur-Weil duality representation theory of the general linear group. And so if you can find a more combinatorial proof of this fact, is another open problem. You can. And the other thing that we use is this character lower bound that I showed. So then we can actually, so we also know one more nice ingredient is that if we take a square partition, another square and a third square, for example, that this is actually bigger than 0. So we do know something, just not enough. Okay. So to end on a positive note with this geometric complexity theory, so the determinant versus permanent is maybe not the best problem one can try to do here. So instead of the determinant, actually one can use matrix, the power of a matrix. It's also universal polynomial, or what's called iterated matrix multiplication. So you just take several matrices, you multiply them together, and you emulating your polynomial through that. And again, actually in these cases, we can actually express these multiplicities, at least in the orbit, not in the orbit closure. So if you take the closure, it becomes a little bit more complicated, but the multiplicities are some hairy expression in terms of Littlewood-Richardson, Kroneckers, and plethysms. I'm not going to write them down because it would be scary. but in principle that the same coefficients are involved because, and the reason why these coefficients are always involved because we have the general linear group acting and the symmetric group acting on this polynomial, so that's what you would expect. So to show that this is not entirely hopeless, that maybe we can find multiplicity obstructions, so we actually can find, even when these coefficients are strictly positive, all of them, then maybe we can still find some inequality. So we did a toy problem. So the problem was about factoring a power sum into linear forms. So one can embed this problem in the same framework of the GCT paradigm. And then we can actually show that there are no occurrence obstructions. So all multiplicities of interests are positive, but there are multiplicity obstructions, and somewhere in this whole hairy business here, we actually had to compute some explicit plethysm coefficients and find that one of them is just one bigger than the other, and that actually gave us the multiplicity obstruction in this case. So in the original we have these two varieties, right? So we're just gonna plug in the other the product of linear forms instead of the determinant. Sorry, the product of linear forms instead of the permanent, and the sum of and the power sums instead of the determinant, and do the same business.
Why do you think that this will enlighten?
So, well, so it's a matter of seeing how GCT can still work in principle. So of course, the problems of interest are these varieties, but we can still distinguish some polynomials using this framework. And then to see what kind of was an example where actually there are no occurrence obstructions like there were in the case for the determinant versus permanent, but one can still find a multiplicity obstruction. So yes, this does not shed any light on VP versus VNP, but in principle there is a whole zoo of lower computational lower bounds than one can apply, and like this is a very simple one of them. But what's actually interesting is that there are some explicit relations for plethysm coefficients that actually are useful here. Okay, so whether or not you buy this the GCT paradigm, it's still important to understand how large these Kronecker coefficients are. So okay, maybe there is no combinatorial interpretation. Maybe we don't have good criteria for positivity, but maybe at least we can figure out how large they are approximately. So this would be asymptotics that is leaving the realm of algebra as it is, but it's still important, and it's also important for this GCT, because if we want to have some inequalities, maybe one way to figure out where to look is to actually to look at asymptotics. So that's another question one can ask about all these structure constants is how large they are. So this is this déjà vu from Pasha's talk earlier. So here are the Q binomial coefficients. So what do they have to do with all of this? So the Q binomial coefficients, when you expand them as a polynomial in Q, their coefficients count the number of partitions inside a rectangle. And it so happens that the Kronecker coefficient of rectangle, and 2 row is actually equal to the difference of two consecutive partition number of number of partitions of K inside the L by M rectangle minus the number of partitions of K minus 1 inside this L by M rectangle. And so using various tricks, we were in combinations of properties like semi-group properties of the Kronecker coefficients and the character bound and other asymptotics, we were able to actually find a lower bound. But later with Robin Pimentel and Steve Meltzer, we actually managed to find the tight exact asymptotics for this number of partitions, which we did with independent random variables. So it has nothing to do with algebra in this case. But the fact that we found this tight asymptotics actually gives us maybe the only non-trivial known asymptotic results for some particular family of Kronecker coefficients. And the question is, of course, are there more? So can one find more asymptotic results? And so to motivate this a little bit better, other than just with this, so here is a question of Richard Stanley showed that the very, very maximal Kronecker coefficient is on the order of square root of n factorial, and the very, very maximal Littlewood-Richardson coefficient is exponential 2 to the n over 2. And the question that he asked is for which lambda, mu, and nu are these maxima achieved? So Richard Stanley asked this question, so it must be important. But then there is a. So let me give you some other motivation. So more of my own. Why would we care about this type of asymptotics results for this structure constants? So here is. So here is what another related somehow topic to algebraic combinatorics, statistical mechanics, dimer model. So Kenyon already talked about dimer. So in this case, these are lozenge tilings of the dimer covers of the hexagonal grid or plane partitions. So one can study the asymptotic behavior. So when you let the mesh size go to 0, you can study how these step surfaces look like and what is the distribution of various types of these three types of lozenges or the sides of the cubes inside and things like that. And one way to study this, if you have like a trapezoidal domain, so you have three vertical lines bounding it and you just vary the right side. So you put lozenges at some positions. The one way to study this turned out to be if you study these normalized Schur functions. And then you can actually extract a lot of this asymptotic behavior just from this normalized Schur function. So now the big question here is, what do you do if you don't have this boundary here, but let's say we have some partition lambda and some partition mu bounding it. So between two sawtooth domains, and we want to do asymptotics there. So more of ragged boundary conditions. So we don't really know. One way to study this would be through using this same paradigm with the skew Schur functions instead of straight shape Schur functions. And eventually, if you want to understand the behavior, it boils down to the study into asymptotics of Kostka coefficients, Littlewood-Richardson, and so on, when these partitions lambda, mu, and nu vary in certain ways. So I'm not going to explain how exactly this works, but there is some connection. So that's a motivation of why should we ask the problem about asymptotics other than just because. So here are some very some partial results on this Kronecker and Littlewood-Richardson. So just using this type of identities, so very basic identities involving Kronecker coefficients, for example, we get that some others, so that the Kronecker coefficients should be the maximal one on the order of square root of n factorial is achieved when all these partitions lambda, mu, and nu have close to the maximal possible dimension, which is what's called Plancherel shape. So if you know the Vershik-Kerov-Logan shape, that the maximal, if we look at the partitions for which we have the maximal number of standard Young tableau, they have this type of limit shape. So this is called the Plancherel shape. It comes from the Plancherel distribution. And it's a theorem that if we want to have partitions with maximal dimension, then we should be close to this shape and so on. So basically, if we are looking for maximal Kronecker coefficients, they all should look like this. The three partitions should look like this. So here are some other results. Let's just not go into this detail. So for the Littlewood-Richardson, one can bound it a little bit better. So if we fix the size of one of the two partitions to be k and n minus k, then this is bounded between this so square root of the binomial coefficient and choose k and some other, and this other lower bound error term. And again one can say that so some of these partitions, at least two of them need to be maximal to have this the Plancherel shape for us to get the maximal size, the Littlewood-Richardson coefficients. But basically, and actually the best result so far, however, was obtained 2 years ago by Belinshi, Alice Guyonnet, and Jieyuan Huang, and they got actually very general upper bound for Littlewood-Richardson coefficients for what's called nice measures, so not really arbitrary lambda, mu, and nu, and this came from random matrix theory. So there is so unfortunately these types of problems probably are not going to be solved with combinatorial methods, but it's even more interesting, I find. And so here are some other bounds. So we can ask this question. So what happens if we are not in this regime where we're looking at this maximal partitions, but in some other regime? So if we have a small number of rows, but not fixed, maybe, then we have an exponential upper bound as from this theorem. And maybe one proof I can show this, that so the way to prove this is to actually see that the Kronecker coefficients are bounded by the number of contingency arrays with marginals lambda, mu, and nu. So contingency arrays, it's three-dimensional box of integer numbers which satisfy these linear conditions for the so for the sum of the various sections. And if you use just this combinatorial identity, which I actually did not write over there, but basically there is a triple Cauchy product identity. We have this identity with the Schur functions, Kronecker coefficients, and on the other side, we have contingency tables. So we get basically for free that this Kronecker coefficient is bounded by T lambda, mu, and nu, just comparing coefficients on both sides and knowing that everything is positive. And then one can bound a number of 3D contingency tables using the machinery of Sasha Barvinok. This is about integer points in polytopes, essentially. These particular transportation polytopes are special. And so the question here is, as you can see, we can do some upper bound. So can we actually do a lower bound? So there are some actually interesting lower bounds that Kronecker coefficient can be bounded from below by the number of 3D partitions. So imagine like 3D stack of boxes where we are limiting the number of boxes in each plane. So each of these marginals. And there is a way to make a construction where this is almost exponential. And we conjecture that actually the largest Kronecker coefficients would appear when we have triples of equal partitions, which are all symmetric, lambda, lambda, lambda. All symmetric, it's still going to be give us the maximum square root of n factorial. And so I'm out of time, so I'm not going to tell you about the reduced Kronecker coefficients, but the take-home message from this is going to be that they're as bad as the usual Kronecker coefficients, so there is no hope there either. And they're also sharply hard. That's thank you.
Thank you, Greta, for a nice talk. Questions?
Yes, we did actually check with Christina Bessenroth. We checked them two years ago, and there are a lot of candidates actually. So the question was what other shapes for the Saxel conjecture have been checked, and the answer is that there are actually many. It's not, yeah. This is work in progress. So. So the question was about Schubert polynomials, and so the complexity, of course, which is what we'd be interested in. There is complexity and asymptotic questions related to Schubert polynomials. And both of them are work in progress, I would say. So. Well, maybe finite groups of Lie type, I don't know. We have no, so they're basically there. So none of these structure constants is known in any tangible way. So I think the Kronecker coefficients would be the easiest. I mean, okay, Littlewood-Richardson for general linear group and yeah. We do, but my graduate student is working on that, so I don't want to. I'm not kidding. Yeah, was there another question? Yeah. So there is, yeah, so the question was when we fix a partition mu, which kind of lambda their tensor square contains mu. We have not looked at that question explicitly, so yeah, no. Vic? So it's this is a very tough question. So I don't know if I should answer it or if I should explain. Maybe maybe Igor will answer some of it tomorrow. So we'll see. Yeah.
Can you say a little more about the reduced Kronecker coefficient, generalized and such?
Okay, I guess let's go to the skipped slide. Okay, so these are the reduced Kronecker coefficients. They are defined by basically taking three partitions and adding a really long first row to all three of them. So that first of all, they're the same size. And eventually when you add the long first row, they will stabilize. So it doesn't matter how many rows you add. They generalize the Littlewood-Richardson coefficients and so on. So there was a conjecture by Kirillov and Klyachko that these reduced Kronecker coefficients satisfy the saturation property. That is, if you scale the partition by an integer and this happens to be strictly positive, then the original reduced Kronecker coefficient is bigger than 0. And we disproved it. So there are a lot of families of partitions for which this does not hold. So here are some of them are listed over there. So basically one column and a square does not satisfy, almost a square does not satisfy this. And the other thing that we did was we showed that basically the reduced Kronecker coefficients behave very much like the original Kronecker coefficients. First of all, in terms of size, they're also the largest one is about square root of n factorial, and in terms of computational complexity, they are basically they share the same complexity as the Kronecker coefficient. Yeah.
Any other questions in the room or on Zoom?
I want to make a scheduling comment for Liz. Thank